I'm presenting on an article titled Repetitive Quantum Non-Demolition Measurement and Soft Decoding of a Silicon Spin Qubit. Some of those terms are a little heavy, so I want to give plenty of background information and motivation first. So, why quantum computing? In December 2018, Google announced that it had achieved quantum supremacy by building a workable 53-qubit quantum computer. Although many experts agree that the term quantum supremacy is a little misleading, researching quantum computers has become a multi-billion-dollar industry, and quantum computing promises to revolutionize the fields of combinatorics, search optimization, factorization, and modeling quantum systems, among others. There are three frontrunners for quantum circuit protocols: IQP, or Instantaneous Quantum Polynomial Time, QAOA, or Quantum Approximate Optimization Algorithms, and boson sampling circuits, which use photons to encode quantum information. All these depend on manipulating a number of entangled qubits, but differ in implementation details and the number of qubits needed to implement useful algorithms. So, what is a qubit? The qubit is the basic building block of quantum information, analogous to a bit in classical computers. An electron spin qubit can be idealized as a point on the Bloch sphere, shown in this slide on the left. And this presentation deals with an electron spin qubit in a quantum dot that is a microscale semiconductor crystal. Here, the same basic principles of quantum mechanics hold, where in this case a measurement of the spin of the qubit changes the state of the particle by the projection principle. In quantum computing, this is called a strong measurement. The contrast weak measurement gathers the expectation of a quantum state without perturbing the state. This is also referred to as quantum non-demolition or quantum non-demolition measurement. What are the current limitations faced by researchers in modern quantum computing? By far the largest challenge in implementing a quantum computer is the need for fault-tolerant systems, or systems with higher gate fidelity. The biggest obstacle to implementing a working quantum computer is the need for operating temperatures below 1 degree Kelvin. This places a physical limit on how many qubits researchers are able to interact with. This year, the first quantum calculation above 1 degree Kelvin was performed at the high temperature of 1.5 Kelvin, using electron spin quantum dots in silicon, which is the same type of quantum particle used in this experiment. So now we're ready to get into the experiment. This measurement method uses an ancilla or secondary qubit to essentially make a copy of the primary qubit. These diagrams show the details of this coding and copying process of weak measurement. First, the logic qubit is written or entangled, and in the third subfigure, this state is weakly copied to the ancilla qubit, which is then read. This process can be repeated a number of times, and a weighted majority vote on the state of the qubit yields the measurement results on the bottom right. That works fine, but to push the boundaries of quantum computing, we need to be able to derive these same measurement probabilities from messier systems. This paper does so by using soft decoding, a more efficient continuous variable readout method. Without noise, the measurements of this system are approximately a unit step function, which can be seen in the top left figure. This measurement space is where most modern quantum computers are forced to operate, and most of them so far have used fixed value error correction. The advantage of using continuous variable error correction comes when a system is messier. This paper simulated a Gaussian distribution of measurement errors, on the bottom left here, and encoded these into their ancillary measurements, and then optimized probabilistic readout methods to create what they call soft decoding. Soft decoding yields mild advantages in single read scenarios and when systems have low signal to noise ratios, like in the top right. But it really excels and paves the way for quantum computers that are able to navigate more realistic environments. The bottom right subfigure shows the reduced error that soft decoded measurements had in this experiment. Together with this year's research into hot qubits, it's safe to say that there will be significant research into silicon spin qubits in the future. Thank you. Here are some references and further reading materials.